Hello, class. We're going to learn about the law of large numbers in the context of random walks. And I would imagine that the audience that is watching this, even if you've never taken even an undergraduate course in probability theory, you've probably heard about the law of large numbers. Maybe some of you even have some vague sense of what it is supposed to mean. And the purpose of today's lecture would be we would focus on random walks, and we're going to apply the law of large numbers to random walks. We will explain what the law says. There are, in fact, two laws. There's the weak law and the strong law. And as you will see, the weak law implies, the strong law implies the weak law. We'll mention both of them. This is also something that people sometimes get confused about, the distinction between the two laws, and we will clarify the small subtle difference that the two laws say. Let's just do a quick recap of what a random walk is. What we do is we're going to start, so we assume that we have a sequence of random variables. These are independent. You think of these as independent coin flips. But more specifically, what we would mean by coin flips is each xn can only take on two possible values. It's either plus or minus 1, because it is a random variable after all. It happens to be a discrete random variable because it only has two outcomes. So these are discrete random variables with only two outcomes. And by coin flips, we want these to be fair coin flips. So we're going to add the condition and the probability that each of these random variables takes on heads or tails is 1/2. Usually when we think of heads and tails, we think of ones and zeros. That's the way we numerically represent heads and tails. Here we think of it as plus or minus 1 for convenience. And we've justified the existence of such a sequence. So that means there exists a sample space on which all of these are defined. They have the required distribution, and they happen to be independent. But often we just begin with this as the starting point without reference to the sample space. And then we define, and then we construct, the symmetric random walk as a sequence Wn. The sequence will begin at time 0 with W0 being equal to 0. So this is just a constant random variable. So this is just a random variable that assigns 0 to each sample point. All of these random variables are defined on the same sample space. And Wn would then be, you would start at W0, and then you would add coin flips. So you're taking random steps to the left and to the right, and you're taking n of them. Why am I writing it like this? Well, because more generally, you can talk about a random walk, and you can add over here, starting at some integer s. So s is some integer. So if you start at s, then you will just modify this, and you would say that W0 is the constant random variable, which is just equal to s. And then the random walk at time n would be W0, so it's s, and then you add to it independent coin flips, n of them, and you randomly walk to the left or right, and you take n steps. We're going to assume that we're starting at 0 because it's very easy to modify this to any starting location. And I should say that to avoid confusion, the entire sequence is a stochastic process. What is a stochastic process? It is just a sequence of random variables. You could say, if you want to, you could also say that this sequence up here that we start with is also a stochastic process. But that's not a very interesting example because this stochastic process, every flip is independent of every other flip. So whatever happens at one moment in time is independent of what happens at another moment in time. So yes, you'd have a sequence, but they have nothing to do with one another. Whereas in this sequence, what happens at a certain moment in time will influence what happens at the next moment in time. So for example, if I know that W5 is equal to 6, then W6 will either be 5 or 7. That's the only thing. If I, however, knew that W5 was equal to 1, then I might not know what W6 is, but at least I know it will have to be either 0 or 2. And that's the point over here, that I guess W5 cannot be equal to 6 unless if you're starting at 0, but you get the point, that if you know the previous value, what happens at a previous moment in time, the next moment in time is not completely determined, but you have some information about where you are. And so this is a dependent sequence of random variables. And that's usually what we mean by a stochastic process. You think of this as something that is a random process. So a stochastic process is also called a random process. You can also say a random process. The word stochastic, as we mentioned before, means random in Greek. And you think of this as some random process that is evolving over time. So this is like a better example of a stochastic process where you have dependency on the past. Whereas it is true, this is also a stochastic process, not a very interesting one because the past is completely irrelevant. So a random walk really represents this entire sequence, whereas when you pick a snapshot in time and each Wn is the random walk at position at time n. So to avoid confusion, the sequence is called the random walk. This is just a snapshot in time. Okay, so this is what we call a symmetric random walk because the probability of moving to the left and right is equally likely. That's where the symmetry comes in. That's the most interesting example of a random walk. If you remove symmetry, as you saw in the simulations, it's a lot more predictable where you end up. Even though you might not know exactly where it is, it becomes less interesting. To use an extreme example, if the probability of moving to the right plus 1 happens with 100%, then you know exactly what Wn is going to be. Now we know, so from the previous lecture we said that if you take the random walk at time n and you look at the expectation of that, this is equal to 0, the expectation. So we expect to be located at 0, right? This is where we start after n steps. We're assuming a random walk begins at 0. If it does not begin at 0, if it begins at an integer s, then this is just going to be s. But for simplicity, we'll just assume we start at 0. So we expect to be at 0. And this should make sense, because if you take 100 steps, because the probability is half of moving into either direction, about half of the time we move to the right, about half of the time we move to the left, and so we expect to be at 0 after n steps. That's what it means, right? That makes sense. We expect to be at 0 after n steps. But it does not necessarily have to happen, right? So we could be a little bit off. Maybe we have one more head than tail, and then we're a little bit off. So let's introduce the following random variable. So let us define an is the sum. So let's look at this random walk. The random walk, it's the starting value, which we assume is 0, plus the sum of all of these. And each of these is heads and tails. So the average, the expectation is the average. This is what's supposed to happen, right? It's what a random variable does on average. But so what is the average of the numbers that you actually see? So you would just take these numbers, plus or minus 1. There's n of them. You will add them up and divide by how many you have. So this is x1 plus x2 plus up to xn divided by n. And now we're going to say that this quantity over here, this is the theoretical average. This is where we're supposed to be. So this is a number. The theoretical average. Whereas this sum, that average, this is the empirical average. This is what we actually get when we move n steps. That's the average that we see. And this is a random variable. Because it's a sum of random variables, right? These are function and variables or functions on the sample space. You're just summing them up, you're dividing. So this quantity, it's random. It will depend on the sample point. So this an. So let me illustrate this to you in a very simple simulation. We're going to use R software to do this. So this simulation is so simple that we do not even need to open up the script window to do it. So here I'm going to type, we're going to type sample. We're going to sample from the list -1 and 1. Then we're going to, how many samples do we want? Let's say we want 100 samples. Replace is equal to true. This just means that, to remind you, it means that we choose these numbers with equal probabilities, and after we choose a number, we put it back in the list and we repeat the random experiment. So if you were to type that in, it will produce for you a random list of heads and tails, plus and minus 1. And because of the random number generator, whatever list you get would be different from mine, unless we set the same seed. Okay? So this is what you would get. Now let me show you what would happen if in front of this command, and let me just show you how I did that again in case you forgot. If you type the up arrow, the up arrow will produce the previous inputted command. If you type the arrow again, it will produce the second previous command. So that's very convenient. So there it is. And I will take the mean. So the mean is just the average of these numbers. So we have 100 random numbers. So we do this random experiment, and then we're going to take the average of all of those. And we get 0.02. As you can see, it does not have to be 0. And I'm going to just repeat this again. Because it's a random experiment, you're always going to get something different. As you can see, the mean is close to being 0. 0 is the theoretical average. That's what you're supposed to see. But in practice, the empirical average of those numbers might be a little bit off. So sometimes you will get it. Now, if you did the homework problem, you should have noticed that the most probable number is 0. This is the most probable number that you have, at least if you have an even number of steps. If you have an odd number of steps, like 101, then it would be impossible to get 0, right? Because you cannot have positive and negatives cancel each other in pairs if you have an odd number. But if you have an even number of steps, the most probable number that you get is 0. However, it is the most probable number, but the probability of it happening is still fairly small. I think it should be approximately, if you did that homework problem, it should be approximately. So there's the exact probability, but the approximate probability using Stirling's approximation, it's the square root of, so it's half, so it's 50 times pi. So this is the approximate probability. So it's about 8% of the time. So 0 is the most probable number, but you only see it 8% of the time. The other numbers are less probable. So something like this would be even less probable. But so if you do it, sometimes you get 0. Most of the time not, but you seem to always get somewhat close to 0. It is conceivable that you get an enormously large number. It is conceivable, for example, that all of these numbers are equal to 1. And then the average would be 1. If all of those numbers are 1, the average would be 1. However, the probability of that happening would be astronomical. It would be 1 divided by 2 to the power of 100. So it is conceivable, but incredibly unlikely. So because of that, the empirical, so here we got a 0 again, the empirical probability is very close to the theoretical, the empirical average is very close to the theoretical average, but there is some margin of error. And that is essentially what the law of large numbers says, that what we get in practice is consistent with what we're supposed to get in theory. Okay, so this is what we have. And now okay, so basically, so this is the simplistic, so basically, the law of large numbers says that an is approximately 0, that the empirical average and the theoretical average are about the same. Now, anytime in mathematics you use an approximate symbol, it's good for heuristic ideas, but how do you make this rigorous? After all, this is a number, this is a random variable, and as we remarked, it is conceivable that the empirical average could be 1. They could all be equal to 1, though the probability of that happening is incredibly unlikely. And this becomes more accurate the larger the n is. And this becomes more accurate the larger n is. That's why we call it the law of large numbers. So, okay, so how do we make this mathematically precise? So I'm going to state it in a more general way than what we have, and then you will see how this more general theorem includes the case of random walks as a special case. So let's remove this and state the theorem. This is called the law of large numbers. And this is the weak version. If you're not sure what makes it weak, that's what will clarify. It will make sense when we talk about the other version of the law of large numbers. So here's what it says. We're going to do this a little bit more generally, not in the context of random walks. It turns out you can prove it a lot more generally, and then the case of random walks is a special case. Let xn be a sequence of independent random variables and each random variable has expectation equal to, let's call it A for average. I know it's common in books on probability theory to denote the expectation by the letter mu for mean, but mu looks like a measure, so maybe we can get confused by that. So let's call it A, so A for average. Now, in the case of random walks, these are independent coin flips, plus or minus 1. So the average of all of these, the expectation of all of these would be 0. So here we're being a little bit more general. And by the way, I should say these random variables, they can be discrete, they can be absolutely continuous random variables, or they can be even of the more pathological type, which are neither, or some mixture of those two. It really does not matter. This is a very general law. It really does not matter what these are. So you have a bunch of random variables. They're independent. They have expectation. They all have the same expectation. So that's the part which is important. They all have the same expectation. And the variance of all of these, so we're going to assume the variance exists, and the variance of all of these is less than or equal to b for some fixed number, for some fixed upper bound. We can assume it's positive. So we're assuming that they have uniform bounded variance. Now, what's interesting about this is the variance somehow sneaks into the statement of the theorem. Like, you would think that since the law of large numbers was all about averages, maybe this is the only thing you care about. But somehow the variance sneaks in. You need to assume something about the variance. You know, this is very common in mathematics, that the thing that you want to happen, the thing that you think, I mean, if you think that something works in mathematics and you try to prove it, you're not able to prove it. And then you realize the reason why you're not able to prove it is because it's actually not true, that you have some pathological example that messes you up. So as you will see, I'm actually going to show you some examples where what we're about to write down is not true without this assumption. So you need to assume that the variance is uniformly bounded. So there's this fixed number that's larger than the variance of all of these. And then you're going to define an, which is the average. You're going to do 1 over n, and you would just average out the first n random variables. Like this. And here's what we're going to say in a rigorous way, that here's the number line, and somewhere on the number line we have A. A represents the average. The average after n, so at any moment in time, the average is always equal to A. But the empirical average after the first n observations, this is what you would do. You just add up the numbers and you divide by how many you had. This is the empirical average. And it could be exactly at A, but it could be a little bit off. So the idea is that you construct a small interval, and the an, it's a random variable, and it's supposed to end up somewhere within that interval. Now, the way you make this rigorous is by using epsilon, just like we do in advanced calculus. We use an epsilon. So we're going to say let epsilon be bigger than 0. Then we're going to look at the probability. So here's what we're going to look at. We're going to look at the random variable an minus a being greater than epsilon, that it falls outside. Okay, so we want it to fall. You think of this band, this interval band, as having thickness epsilon. And we want to say that an has to fall somewhere within this band. And we're saying if it falls outside the band, then we're on the other side. Should you use greater than, or should you use greater than, or should you use greater than or equal to? It really does not matter. It's not going to affect it. There are some books that will write it with a weak inequality. Some will write it with a strict inequality. It does not matter, because if it's true for a strict inequality, you can just, and since epsilon can always be made smaller, it will be true for a strict inequality as well. So it does not matter. You're going to calculate the probability of this. Now, if you're confused by what that means, all this means, this is just a shorthand way of saying is, you're going to look at the sample space, which we never even bother to reference because we do not need it, but we're going to look at the sample space. We're going to look at all of the sample points which satisfy this condition. So the condition would be that an of omega minus a is greater than or equal to epsilon, and that will give you an event. So this is an event. This is the collection of sample points that satisfies this inequality. And then you calculate the probability of that event. Instead of writing all of that out, we're sloppily write it like this, and we understand that this is the set of sample points which forms the event, and then you're calculating the probability of that. So the probability of that event is supposed to be small. The probability that you fall outside that interval, it's supposed to be small as you make n larger. So we say that the limit as n goes to infinity of whatever that probability is equal to 0. That's the way you make this rigorous. Okay? And this also includes the case of random walks as a special case. So the above general version includes the special case of random walks. Why is that? Well, because when you have random walks, each of these is plus or minus 1. Their expectation is 0. And the variance of all of these is 1. You can work it through, but you had that as a homework problem. So the variance is uniformly bounded by one constant. In this case, the constant is 1. And then you just apply. So a is equal to 0 here. And then you're saying the probability that the empirical average deviates away from 0, so it's an absolute value bigger than or equal to 0, the probability of that will approach 0 in the limit. So no matter how small you make that epsilon, so this will just mean that, so here's 0, we create a tiny little interval, and we're saying the probability that the empirical average after n steps falls outside that interval, outside that bound, is unlikely to happen. It could happen, but it's very unlikely. And the larger you make the n, the more unlikely it becomes. So that's what we're saying, that if you were to calculate whatever that probability is for a certain value of n, and as you were to increase it in the limit, it will go to 0. So that is what we're saying. So it therefore has to end up somewhere over there. So it could end up, but the probability just keeps on diminishing smaller and smaller, and that's why we're putting in a limit over here. So this is the law of large numbers, the weak law of large numbers. We will state the strong law of large numbers afterwards, but this is what it says. And one thing you notice is something that might be a little bit unusual, and it's the appearance of variance. So this seems a bit unusual. You look at that and you say, the law of large numbers says only says something about averages. So why does the variance appear as a condition? Right? This is a little bit unusual because it's all about averages, and it's about the way the probability of averages behave. We're not in any way interested about the variance, about these random variables or the variance of their empirical average, but somehow you need that condition in the statement of the law of large numbers. And this is one of those instances in mathematics that you have, what you basically have is you have something that's a bit pathological, something that you think should happen does not actually happen. And I'm going to show you an example of what violates this. I'm actually going to show you two examples that will violate them. One of them, it's the easier one, I'm going to show it to you, and then I'll put another one on your homework. So this will be a pathological example to show you that the law of large numbers does not need to be true if you violate this bounded variance assumption. Now let's look at some pathological examples. Pathological examples that contradict. Now, I should say contradict in quotation marks because you're not able to contradict the law of large numbers. It is a theorem. So what I mean is that some of the conditions that you need are no longer satisfied. So the law of large numbers has two really important conditions. One of them is independence, and the other one is bounded variance, uniform bounded variance. So let's talk about independence first, that contradict the law of large numbers. So in this example, so let's do independence. Let's say x1 is plus or minus 1, and the probability that x1 is plus or minus 1 is 1/2. So a coin toss. And then for n greater than or equal to 2, every other random variable in our sequence is identical to x1. So in other words, if we get heads, then our random sequence would be 1, 1, 1, 1, 1. That every next value in this random sequence is determined by the first one. And if we get tails, then we only have this random sequence. So this is the extreme opposite of independent coin flips. It's where every other coin just follows from the first one. Okay, so what happens next? So then the expectation of each xn, well, that would be 0. And the variance of each xn is 1. So at least the variance condition is satisfied. But of course, we are violating independence. And an in this case, the average of the first n tosses, would then be, well, it's the same random variable. From x2 to xn, it's always the same. So it's n x1 over n, so it's just x1. So there we go. So that would just be x1. Okay, and then what happens next? So what happens next is then we have to check. So we're basically asking the question for epsilon greater than 0, is it true that the limit as n goes to infinity of the probability that an greater than or equal to epsilon goes to 0? So let's pick a particular choice for epsilon. So if epsilon is 1/2, we're choosing 1/2 not because that number is 1/2, but we want to choose something smaller than the random variable because an that's just x1. So we're asking, is it true that the limit when n goes to infinity of the probability that the absolute value of x1 is greater than or equal to 1/2? Is that equal to 0? No, because x1 takes on two possible values, 1 and -1. Regardless of what it takes, the absolute value of this is always 1. So this is true for every sample point. For every sample point, this is satisfied. So this is the probability of the entire sample space. We do not even care what the sample space is. Just the probability of the entire sample space is 1. So this is just 1. And so we have the limit of the sequence of 1s, which is not equal to 0. And as you can see, it violates the law of large numbers. Not really, of course, because the law of large numbers requires independence, but you can see why you need independence here. Now, in our next example, we're going to violate the variance condition. This is example 2. And here I have to warn you, warning, you need to be familiar with the properties of a normal random variable in order to understand this example. So I'm going to show you this example, and if you're not familiar with these properties, that's okay, because I'm going to have another one on the homework that will do it a little bit differently, but it will take a bit more work. Now, previously we talked about what it means for a random variable to follow the normal 0-1 distribution. This means that the probability distribution, so this is a probability measure on the real line, and it has a PDF. Well, let's do it like this: the PDF. So the PDF, the probability density function of x, is the function that we call phi of s, where phi of s, this is what we refer to as the standard normal density. It's given by this. And then if E is a Borel set on the real line, then the probability that the random variable falls into that event, just say an interval for simplicity. So if the probability that the random variable falls, its value forms into some kind of interval, is then given by integrating over that interval, or more generally over that Borel set, phi of s ds. So it's a random variable whose probability density function is given by this very special function. I know that it's very mysterious. It's unclear where this even comes from. Like, did people just randomly made it up, or did they have some motivation that led to them? And of course, there was motivation that led to such a function, and we'll see later on where it comes from. But that's what it means to be a normal 0-1 random variable. Now, the significance of 0 and 1 is that the expectation of x, and you were asked to show this on one of the homework assignments, is 0, and the variance of x is equal to 1. So that's what these numbers represent. So the first number is for the expectation. The second number is for the variance. Now, I just want to caution you a little bit. When we say uniform 0-1, here the meaning of 0 and 1 are different. This is just an interval. This is not an interval. This is the expectation. That's the variance. The expectation of the uniform is 1/2. Okay, so this is normal 0-1, and the picture for the probability density function would be that this function phi, it goes something like this. Now, you could be a little bit more general, and you can replace this number by anything. So this, in general, this could be any number. Let's say 3. And the second one could be any positive number, let's say 2. Then the idea is you're shifting this so that the center is going to be at 3. So you just shift it over at 3. And because you want the variance to be bigger than 1, that means you're going to make it be more spread out. So it's just going to be like more spread out, something like that. Now, if you actually want to look up what this adjusted probability density function is for a different type of normal, you can look it up. You can go like Wikipedia, you can just look up normal distribution. They will show you more generally what that is. If you've never seen it before, that's okay, because like I said, for the purposes of our class, the one that's most important is normal 0, 1. But here we're going to assume that we're going to work with more general normals. So here's what we're going to have. So we're going to have a sequence xn. These are going to be independent random variables and every xn will follow, the distribution of xn will be of the kind normal 0, comma, and the variance is going to be 2n minus 1, an odd number. The significance of this you will see. It's going to be convenient to make it be odd. So x1 will be normal 0, 1. x2 will be normal 0, 3, then 0, 5. So all of them have mean 0. So each xn has expectation equal to 0, but the variance of every one of them is 2n minus 1. So this is there is no uniform bound on the variance. And now we're going to add them up. So then an, so you see the condition of the law of large numbers is almost satisfied. These are independent random variables. They all have the same expectation, in this case 0, but their variance cannot be uniformly bounded by one single number. So let's see what happens with the empirical average. So if we take the average of these, this is what we get. And now we're going to use a fact about, so this is like a fact. It is a well-known result in probability theory. I'm not going to prove this because I imagine this is something that maybe they show you in like a probability theory course. That a linear combination of independent normal random variables. So a normal random variable, it's just a random variable whose PDF, that has a PDF, and its PDF follows that normal density function, is again in the normal family. So a linear combination of independent normals. So that would mean that an, if you are willing to accept that well-known fact, if you're not willing to accept that fact, then do not worry. I will put something on the homework that will not use it. The example will be a little bit more complicated, but I think this is such a nice example. It's a nice example. It's not too bad. This is like the only thing you have to accept about it. So that would mean that an is a normal random variable. You see, it's a linear combination. In fact, the weighting coefficients are all the same. This will be normal. So it'll be normal of two parameters. There'll be some number, comma, some other number. To find out what those numbers are, you just use the expectation and the variance. So we observe that, okay, so the fact that I know that the average follows a normal distribution again, this is just a linear independence fact, that these are independent normals and you're taking a linear combination, and when you take a linear combination, this an will be normal itself. So I'm going to observe that because it's normal, it has an expectation and it has a variance, so let's compute what that is. That the expectation of an, so an expectation of the sum is the sum of expectations, and you can factor out the constant. So it'll be the expectation of x1 plus the expectation of x2, expectation of xn, and all of these are equal to 0. Okay, so that means that this number has to be 0. let's find the variance. So the variance of an, that would be the variance of 1 over n, and then you have the sum of these. And now I have to use a fact that I never mentioned before because we never needed it, but variance is very similar to expectation, that you're allowed to factor out a constant. But so this constant 1 over n can be factored outside, but with variance, because everything is being squared, when you factor it outside, it will get squared. So this is going to be 1 over n squared, and then you have a variance of a sum. And now we use the question on the homework that you were asked to show that a variance of a sum distributes when the random variables are independent. So this is 1 over n squared, and then we have variance of x1 plus up to variance of xn. So this is 1 over n squared, and the variance of x1 is 1. It's odd number. The next one is 3, the next one is 5, and it will go up to this way up to 2n minus 1. Okay, so what happens next? Now we're going to use a very nice identity that the sum of odd numbers, and this is the reason why it can be odd, adds up to a perfect square. That's actually n squared. If you do not believe me, let me just show you what I mean. 1 is equal to 1 squared. 1 plus 3 is equal to 2 squared. 1 plus 3 plus 5 is equal to 3 squared. 1 plus 3 plus 5 plus 7 is equal to 4 squared, and so on. This is very easy to prove by induction or whatever method you like to use. Very simple. It's a well-known fact. It's one of those interesting things. You can even probably come up with a proof by like drawing dots or something, that if it's an odd number, then you can fill in the odd numbers into the appropriate slots, and you end up building a square out of them. So there's all sorts of proofs you can come up with, but believable. So it's 1 over n squared times 1 over n squared, so it's equal to 1. So that's quite nice. So hence, an will be normal 0, 1. So it'll be standard normal. And now let epsilon be bigger than 0. So then we're going to calculate the limit as n goes to infinity. And we're going to see what happens when we try to use the law of large numbers. We're going to look at the probability that an minus its average, in this case it's 0, is greater than or equal to epsilon. So by using the complement, you can say that this is the limit. Well, let's just say this. So this follows the normal 0, 1. So this is what you're going to say. This is just the limit n goes to infinity. How do you calculate the probability that a random variable falls within that interval? So this is just going to be the interval from epsilon to infinity. I'll write it like this. Integral from epsilon to infinity. And then we're going to integrate the standard normal density function. And we're going to multiply it by 2 because of symmetry. It's symmetric. You're on the positive side and then the negative side. So as a picture, what we're saying is, here is the standard normal density function phi. Here you have an epsilon somewhere, and you want to find the probability that you fall in that region. Now, we do not care what this number is. The point is, this number does not depend on n. You see, there's no dependence on n. So whatever this is some positive number. This is equal to the limit as n goes to infinity, and this is some positive number. We do not care what it is. It's some positive number. So whatever this is therefore not equal to 0. The law of large numbers will tell us that the limit of those probabilities should converge to 0, but it's not. It's just some positive number. It could be small, but the point is it's not equal to 0. It's a positive number that depends on the epsilon. So as you can see, we have, quote, contradicted, not really, because we're not satisfying the variance condition, the law of large numbers. So I think this is a nice example. I'll give you another one in the homework, and you can try to work it out. So now this brings us to the question of, how do you prove the law of large numbers? We see that you actually need the variance assumption that it's uniformly bounded. With that assumption, how do we then go ahead and prove the law of large numbers? Now we're going to discuss the proof of the law of large numbers. And this is, as we've said, is the weak version. It's not clear at the moment why this is the weak version, but it will become clear when we state the strong version afterwards. And interestingly, the proof is very short. Like, you would think that this is something difficult to prove because it's a fairly general statement about all random variables, but as you will see, the proof is actually quite short. Now, just because the proof is short does not actually mean it's easy to find. There's a little bit of cleverness that is involved to make it work. And the idea is you need to use, so we need what is known as a concentration inequality. Now, what is a concentration inequality? Basically, it's an inequality. This is an inequality that puts a bound on how far a random variable is away from its expectation. Concentration, how much is the random variable concentrated? And in the next lecture will be dedicated to concentration inequalities. But in this lecture, we will use the simplest type of inequality. This is by far the simplest one that you have. There's more difficult ones, more advanced ones, and they're all what are known as concentration inequalities. So the inequality that we're going to look at, here's what it says. It goes by the name of Markov's, or depending on what author you use, Chebyshev inequality. Basically, what I imagine happened was, in the early days of probability theory, one of the prominent mathematicians who contributed to probability theory was Andrei Markov and also Chebyshev. And Markov probably written a lot of papers on probability theory where he kept on using a certain inequality a lot of the time. It's sort of like the equivalent of the triangle inequality in advanced calculus. It's very simple, but you use it a lot. It's very useful. So this is one of those inequalities which is very, very simple, but it is used a lot in the subject. So what does the inequality say? And also, it probably might depend on the author. Maybe some people call it Chebyshev inequality. But here's what the inequality says. It says that assume x is a non-negative random variable and we have an arbitrary cutoff point. Let me draw a picture first. So this is as we said, this is the simplest type of concentration inequality that we have. So here's a picture. This is the real number line. Here is 0. Our random variable, it produces for us random numbers that are non-negative, so numbers that are over here. So x has to be over there. And let's say the average is right here. That's the average. The expectation. So we expect that the random variable should be somewhere in the neighborhood of the average. It should be somewhere over here. We might not know exactly where it is, but it should be somewhere over there. So we're saying let's take an arbitrary cutoff point. Let's call that number t. Maybe it's to the left or right, but let's say t is over here. So what would be the probability that we end up somewhere over here? So away from where we expect to be. And t is a positive number. Then the probability that our random variable is greater than or equal to t, and it does not matter whether this is a strict or weak inequality. just depending on how people write it. We can put a bound on how big that probability is. This is not supposed to happen. It could happen, but it's not supposed to happen because we're far away from the expectation. So it's going to be bounded by the expectation of x divided by t. Assuming the expectation exists as a finite number, though because the random variable is non-negative, if you were to calculate its expectation and it's non-negative, if it does not exist, then it's infinity, and then you're just saying this probability is bounded by infinity, which is certainly correct. So this is Markov's inequality. Chebyshev's inequality is almost the same thing, but what it does is that it allows the random variable to be negative, and it is both on both sides, and it uses the variance instead of the expectation. It's almost the same thing. I mean, you can look it up what it says. So for example, to show you an example, if the expectation of x is equal to 1, we have a non-negative random variable and the expectation is 1, then the probability that x is greater than or equal to 5. So this is not supposed to happen. The expectation is 1, so we expect the random variable to be somewhere around 1. That's why we call it concentration. How much is it concentrated at its average? And this is a tail. You can call this a tail. The probability of a tail. So if you choose the cutoff point to be 5, and you're asking what's the probability that the random variable is greater than or equal to 5, we might not know exactly what it is, but it's certainly bounded by the expectation of x divided by 5. And since the expectation is 1, this is 1 divided by 5, so it's 0.2. So the reason why this is a nice inequality is because it tells us automatically that the probability of this taking place, we might not know exactly what it is, but it's certainly bounded by 0.2. Okay, so the nice feature of Markov's inequality is that it is very general. It does not require any more information. We're not assuming that the random variable is discrete or absolutely continuous. We're not using the probability density function. We're not using any of that. None of that is being used. It's a very, very general inequality. Every random variable, no matter what you will choose, will automatically satisfy this. Now, maybe for some random variables, this probability could be substantially smaller than 0.2, but this is a bound that all of them will have to satisfy. And the proof of this inequality is on your homework, which is linked at the video description. I give you a hint how to prove it. It's actually very easy to prove. It's a very short inequality, and you'll just work it out. And now that we have Markov's inequality, we can go ahead and prove the law of large numbers. So proof of the law of large numbers. As proofs in analysis, we're going to say let epsilon be bigger than 0. So if you ever taken an advanced calculus class, all of your proofs pretty much begin with let epsilon be bigger than 0. Okay, so, and an is this. It's the average of these random variables where each xi has expectation equal to a. Then the expectation of an would be the expectation of the sum so you can factor out the 1 over n, that's a constant, and then it's the expectation of the sum of these, so it's the sum of a's, so this is just equal to a, because it's n times a divided by n, so it's just a. So the expectation of an is a. So the probability that an minus a that this is greater than or equal to epsilon in absolute value. So let's rewrite this where we put in a square. And actually, this is basically what they call Chebyshev inequality. Chebyshev inequality is when you rewrite Mov's inequality by using a square, and then the variance comes up instead of expectation. But it's all, like I said, the two inequalities are almost identical to each other. They're just different names of essentially the same thing. So this is the probability. So you can rewrite that. You can just square both sides. The fact that you can square both sides is due to the presence of this absolute value. So you can square both sides. So you're saying the probability that an minus a squared greater than or equal to epsilon squared, right? If this is true, then that is true. And if that is true, then this is true. So you can just rewrite it like this. And here we're going to use Markov's inequality. So this is then bounded by less than or equal to, and here we're using Markov's inequality, because this is a tail. This is the tail probability. We want the probability that this random variable, so this is a non-negative random variable. This is a non-negative random variable. I know you can say this is also a non-negative random variable, and you're absolutely correct. But we want to square it for reasons that you're about to see, because that's the way we end up picking up the variance when you end up squaring it. So by Markov's inequality, the expectation of this non-negative random variable, so this is bounded by the expectation of an minus a squared divided by epsilon squared, divided by the tail, right? That's the tail. The expectation divided by the tail. Okay, now look at this. But the expectation of an minus a squared is equal to, and this is by definition, that's just the variance of an. How do you find the variance? When you have a random variable, how do you find the variance? You take the random variable, you subtract away from that random variable. I'll write it down here. So recall, if the expectation of x is equal to a, then the variance of x is equal to, and this is by definition, you do x minus a parentheses squared, and then you take the expectation of the whole thing. That's the definition of variance. That's exactly what we're doing. You see, we have shown that the expectation of an is equal to a also. And so an minus a squared, the expectation of that random variable, is by definition the variance of an. However, the variance of an, so let's write this out. The variance an, so an is 1 over n, and it's the sum of these independent random variables. Now, as we already remarked before, when you have a constant inside a variance, you can take it out with a square. So that's 1 over n squared. And we're left with the variance of x1 plus the variance of xn. And this is less than or equal to, and this is where we use the fact that the variance is bounded, that this one is bounded by b. All of these are bounded by b. There's a uniform bound on the variance. And so when we add this up, this is nb divided by n squared. So we end up with b divided by n. Okay, so we have shown, so to summarize, we have shown that the probability that an minus a in absolute value greater than or equal to epsilon is bounded by, so let's scroll all the way back up. So we started with this probability, and we saw it's equal to this, and it's bounded by Markov's inequality by that. But the expectation is the variance. And the variance is 1 over n squared, and then you add up, so the variance of a sum of independent random variables is the sum of their variances. But each of these variances are bounded by b. So again, we're bounded by this. So in the end, we're dominated by b over n. So whatever this probability is, it's dominated by b over n. So thus, as n goes to infinity, we see that the limit, so if you calculate this probability, whatever it is, as n goes to infinity, it will have to give you 0. You see, it's because it's a fixed number divided by n. So this is going to 0, and so whatever that limit is, it has to be 0. So this is the proof of Markov's, this is the proof of the law of large numbers using Markov's inequality. It's a nice proof. It's not difficult whatsoever. The clever part of the proof, really, this is like the clever part of the proof, is to rewrite this using a square. You have to rewrite it using a square. And after you rewrite it using a square, then you apply Markov's inequality, and from there everything presents itself. But this is not something that typically enters one mind when you try to prove this. So this is why this is probably the most difficult step in the proof. But the proof is quite short, and the proof is quite nice. So this is the weak law of large numbers. Now we want to move on and talk about what is known as the strong law of large numbers. Now we're going to get to the strong law. Let's set the assumption that, so I'll make a definition here. Let xn be a sequence of random variables with all of them having the same expectation. And we're going to construct an to be the empirical average obtained from the first n observations coming from these random variables. So this is the definition. Is going to have two parts. The first part is going to say the weak law of large numbers says that for any epsilon bigger than 0, if we calculate the probability that an minus a is greater than or equal to epsilon in absolute value, and then we calculate the limit of those probabilities, that gives us 0. Okay, so this is the definition of the weak law of large numbers. You will notice I'm not assuming anything about this random sequence other than the fact they all have the same expectation. We've proved that if they also happen to be independent and they have bounded variance, then we have this. But more generally, we can talk about the weak law of large numbers for any sequence, all of which have the same expectation. So this is what we call the weak law of large numbers. Now, the strong law of large numbers, the strong law of large numbers says, and basically what this law is that it allows you to set epsilon is equal to 0. So in the weak law, epsilon is a positive number, but in the strong law of large numbers, you can set epsilon is equal to 0. But I want to just explain to you that this will actually not be true the way it is currently stated. You cannot just set epsilon to be equal to 0. Because, for example, so if every xn is plus or minus 1, and this is an independent sequence, then the probability that an, so in this case, the average is 0, the probability that this is, well, I guess I should say strictly positive, perhaps. I know I've written it with a weak inequality, so here it would make more sense to write it with a strict inequality, that this is positive. So this is just another way of saying that this is the probability that an is not equal to 0. It's a non-zero number. Well, what is this probability is? Well, we know from a homework problem with Stirling's approximation that the probability that an is equal to 0 exactly. So if n happens to be an even integer, then the probability that the random walk is equal to 0, this is the most probable outcome. And this probability is approximately, it's some constant divided by the square root of n. There's like a pi in there and all of that, but the constant is not so important. The important point here is this, so that the probability that an is not equal to 0, would therefore be approximately equal to the complement of that, 1 minus c over the square root of n. And in the limit, as n goes to infinity, the limit of that is going to be 1. It's not going to be 0. So you cannot just set epsilon is equal to 0, calculate the probability, and then take the limit. Because usually what's going to happen is it's going to converge to 1 in many cases. Not always, but in this particular case, it will converge to 1. So something is wrong when you just set epsilon is equal to 0. So the other distinction in the strong law of large numbers is you set epsilon is equal to 0, but you also do the limit first. So the limit is actually part of the event, and the probability is on the outside. So you interchange those two. So the strong law of large numbers says that if you calculate the probability that the limit of an is not equal to a, so here epsilon is a margin of error between the empirical average and the theoretical average. And in the strong law of large numbers, you're saying there is no margin of error. They are exactly equal in the case where the limit goes first and then you take the probability. If you're confused by what that means, this just means, this is just a shorthand way of saying, this is the probability. You're going to look at the event of all sample points such that the limit of an on those sample points. So the moment you evaluate this random variable at a sample point, you're going to get a sequence of numbers, and you're saying that sequence of numbers does not converge to a, and that would be the event. Then the probability of that event happens with probability equal to 0. So to illustrate what I'm saying in the context of random walks, so in the context of random walks, we're saying the limit that an is not equal to 0 happens with probability 0. So for example, so to illustrate, let's produce a sequence of heads and tails where the empirical average does not converge to 0. So for example, if you have the following infinite sequence of heads and tails, let's say they're all heads, then you can calculate that an, let's say this is your sample point, that an on that sample point will always be equal to 1. Because the average of the first 2 is 1, the average of the first 3 is 1, the average of the first 4 is 1. So that will always be equal to 1. And as you can see, the limit of the sequence, it converges to something that's not equal to 0. Okay, so this would be an example of a sample point that falls into this event. The thing is, yeah, so you're going to have infinitely different sequences. So another example of an infinite sequence is maybe it goes like this. It's heads, tails, 2 heads, then 1 tail, then 3 heads, then 1 tail, then 4 heads, then 1 tail, and so on. So if your sample point is equal to this, then if you were to calculate the limit of these, you will actually get that something diverges. Because in the case of random walks, you just convert this to plus and minus 1. Plus 1, plus 1, minus 1, plus 1, plus 1, plus 1, minus 1, plus 1, plus 1, plus 1, minus 1. So if you were to add these up, no, well, actually, you're going to get something that also converges to 1. Because you can just see that if you were to add up the first 100 of them, most of them are going to be 1, and only a few of them are going to be negative 1. So the ratio, it'll be something like 90 to 100 or something like that. So as you keep on increasing the length of the sequence, in the limit, you're going to get something that actually converges to 1. But you can come up with other sequences where the limit oscillates between 1 and negative 1, and it does not really converge to anything. So like, for example, let's say it went like this. It goes heads, so that would be 1. Then it's tails, so that would be 0. The sum of those two would be 0. Then you have heads 1, 0, 1, 0, and so on. So for this sequence of heads and tails, if you start calculating these averages, the sequence of averages, they're just going to oscillate between, well, that also does not work. Yeah, that also does not work. So I'm thinking about maybe something like this. So maybe you have heads, so that would be 1. Well, you can try to figure something out. I'm not going to try to figure it out over here. I'm basically saying you can come up with a sequence of heads and tails so that if you start calculating these ANs, you're going to get an oscillatory sequence that jumps between positive and negative numbers without even converging anywhere. And the point of the strong law of large numbers is that if you were to look at the event consisting of all sample points, so in this case the sample points are infinite tosses of heads and tails, if you're going to look at the event of all these sample points, of all these different configurations where this AN sequence fails to have a limit of 0, then the probability of that event, that would be an event of probability 0. So even though it is possible to come up with a sequence of heads and tails so that the limit of these does not converge to 0, the probability of that entire event taking place will be almost impossible. It will happen with probability 0. That's what we say. So you can find, so there's certainly sample points that satisfy this condition, but those sample points as an event, they form an event of probability 0. That's what it says. And I would like to just say that this law, so in practice, we use the weak law of large numbers. The strong law of large numbers is a mathematical idealization when we do something up to infinity. Like in real life, you do not have an infinite collection of heads and tails. So in real life, this is not something you can really verify, because anytime you have a collection of random variables, it's always going to be a finite collection. So this is sort of like a mathematical idealization. In practice, this is normally what we do, because when you calculate this event, you're technically only calculating this event up to time n. So you have a finite amount of data that you're dealing with, and then you can calculate the probability of that taking place. The only thing that matters is what happens in the first n outcomes, and so this is more suitable for the kind of things you do in real life. But this is more like an idealization of what you're trying to say. So this is the strong law of large numbers. Basically what it is you're setting the margin of, maybe it would be better to use a strict inequality, because by setting epsilon to be equal to 0, you're saying these are not equal to each other. So you're making epsilon be equal to 0. But then the other distinction is the limit goes first and then the probability goes second. You're interchanging probability with limit. So this is the strong law of large numbers. And let's therefore say a theorem about this. Let's write some theorems down relating to this. Theorem. So this is part 1. A sufficient condition to satisfy the weak law of large numbers is for the sequence to be independent and of uniform bounded variance. So this is what we proved. It's not a necessary condition. You could come up with examples of sequences that might violate the bounded variance assumption, but the weak law of large numbers still continues to hold. And you can have situations where this is not even an independent sequence. We will see situations later on where you have a dependent sequence, but it still satisfies the weak law of large numbers. But this is like a sufficient condition. If you assume independence and you assume something about the variance, then this conclusion of the weak law of large numbers is satisfied. Now for part 2, this is going to be a sufficient condition to satisfy the strong law of large numbers is for the sequence to be independent. So it's an independent collection of random variables. And the interesting part here, as you will see, we're not going to assume anything about the variance whatsoever. Rather, the assumption is going to be that all xn have the same distribution. We call this identically distributed. So these are different random variables, but they have the same distribution. In the case of random walks, that's exactly what's going on. Our independent sequence of random variables, they're different random variables, but they all have the same distribution. Every xn can only give you 2 possible outcomes, 1 and -1, and both of those outcomes happen with equal probabilities. So if you assume that this is an independent sequence of identically distributed random variables, then you do not even need to assume anything about the variance whatsoever. The strong law of large numbers will be satisfied. And for those of you who are interested, this is hard to prove. So we will prove it, we will prove this in the special case of random walks. Because after all, we are talking about random walks. The proof of part one, which is more general than what we're doing with random walks, is actually not that much harder to prove. But this one is actually a lot more difficult to prove. So we're going to have a specialized proof that will work for random walks, but it will not work in general. You need to try harder to make this work out. And the third thing I would like to say, this is part three, is that the strong law of large numbers implies the weak law of large numbers. It's not true the other way around, but that's why we call this the strong law and the weak law. If you know that a sequence of random variables satisfies the strong law, then you also know it satisfies the weak law. So this goes back to what I was saying. This condition of being uniformly bounded in the variance is sufficient, but it's not necessary. You can take any collection of random variables, all of which have the same expectation. They're independent, they all have the same distribution, but they do not even have a variance. The variance is not even defined, but the strong law of large numbers will be satisfied, and then from there it will follow that the weak law of large numbers is also true, except it will not follow from the proof that we had, because the proof that we had required the uniform boundedness assumption. Okay, so now as far as the proof of this is concerned, this one we already proved. I'm going to discuss this one right now. We're going to discuss why this is true. We're going to show that the strong law of large numbers implies the weak law of large numbers. And then for part two, I'll give you a half of a proof. So by half of a proof, what I mean is, instead of proving it in the most general possible way, which is the way it's presented over here, we'll prove it in the special case where this is a sequence of independent coin flips, which is what we're doing with random walks. So that's going to be our plan. So we start with part three. In order to understand the proof of the two different laws of large numbers, how one implies the other, we need to do a quick review of convergence of sequences, something that you do in advanced calculus. We have a sequence of real numbers, does not matter where it starts, and the arrow here means converges to some number a. What does this mean? It means that for any epsilon, you can find there is an integer, we could call it n0, so that the difference between every term in the sequence and its limit, which we're calling a, is within epsilon, and this is for all n bigger than or equal to 0, bigger than or equal to n0. This is the cutoff point. And the idea here is that if this is the limit, and this is a1, a2, a3, a4, a5, a6, the idea is that if you create a interval centered at a of thickness epsilon, that's your margin of error, the sequence does not have to become equal to a, but it gets arbitrarily close to a. So you choose the epsilon, and then you're saying that from some point on, maybe not immediately right away, you see, not immediately right away, but from some point on, in this case, that happens at 5. So from 5 and onwards, this condition is satisfied. Now, I'm going to rewrite this in an alternative way that would be convenient for us. Alternatively, we could also say that that for any epsilon bigger than 0, the inequality that an minus a in absolute value is less than epsilon is satisfied for almost all n. What do we mean by almost all? It just means that only a finite number of exceptions. And this should make sense, because if this inequality is true for all integers beyond n0, then it will mean everything from 1 up to n0, it may not necessarily satisfy the inequality. So that's where you have the exceptions. So you have finitely many exceptions. But beyond that point, it all becomes true. Okay? So for example, the inequality, let's say I tell you n squared is bigger than 10. This inequality is true for almost all positive integers n, because there's a finite number of exceptions. What are the exceptions? 0 squared bigger than 10, not true. 1 squared bigger than 10, not true. 2 squared bigger than 10, not true. 3 squared bigger than 10, not true. But when it's 4 squared, this is true, and from that point on, all of them become true. So there's only a finite number of exceptions. And now we have to talk about something that's actually a little bit more complicated, what it means for a sequence not to converge. If a sequence of numbers, let's say the sequence starts at 1, it does not really matter, does not converge to a number a, then what does this mean? Then there is some epsilon bigger than 0. You see, when a sequence converges to a limit, the inequality that an is within a, that an is within epsilon of a, has to be satisfied for almost all n. And that has to be the case for every epsilon. So when a sequence of numbers does not converge to some number, then that means there is an epsilon, at least one epsilon, that will violate the convergence condition. So there is some epsilon so that an minus a is bigger than or equal to epsilon. And here's the part that you have to be very careful about. Instead of saying almost all, you would rather say for infinitely many n. Sometimes people say infinitely often. So there is an infinite number. So the inequality is not satisfied. So rather you have this. So for example, the inequality that negative 1 to the n is bigger than 0 is true, and you would say infinitely often. That there's an infinite number of n's that make this true. For instance, the even integers. This is true for the even integers. We do not say for almost all n, because that's not true. There is no point beyond which this inequality becomes true. However, it is true infinitely often. There's an infinite number of integers that will satisfy this. Because that's the opposite. You see, this is the opposite of what it means to be almost always. Almost always means there's a finite number of exceptions. So the opposite of that is that there's an infinite number of exceptions. So there's an infinite number, there's infinitely many n that satisfy the opposite inequality. So they violate the epsilon condition. So I mentioned this because we're going to be using it within the proof. So here's what we're going to prove. We're going to assume we have a sequence of random variables. All of them have expectation A. And the probability of this, the limit when n goes to infinity of an not equal to a, happens with probability 0. I should have said that an is this average. And what does this mean? This just means the event. So if you define the event of points in the sample space so that the limit of this sequence an applied to that sample point. So by applying this random variable to the sample point, this is now a sequence of real numbers, and the limit of that sequence of real numbers does not converge to a. So if we define an event, a little bit unfortunate, there is an e over here and there is an e over there, but we can tell them apart. So this is going to be our e, then the probability of that event occurs with probability 0. So that's what we're saying. That's what we're assuming. We are assuming the strong law of large numbers. And what do we want to show? We want to show that if epsilon is bigger than 0, then if we were to calculate these limits coming from the weak law of large numbers, then these are equal to 0. We want to show this is satisfied for every positive epsilon. So basically, if a sequence of random variables satisfies the strong law of large numbers, then it also satisfies the weak law of large numbers. So that's what we want to prove. So how do we do this? Well, let me define the following event. So let us construct. So here's the proof of this. We're going to construct the following event. Let's call this event E subscript epsilon. And this is going to basically be a subset. So here's the thing. E consists of all sample points such that this sequence does not converge to A. So if it does not converge to A, then that means there is some epsilon that violates the convergence requirement. That epsilon will therefore represent all those sample points that violate this convergence requirement at the level epsilon. So to write it out more carefully, this will consist of all sample points with the property that an of omega minus a is greater than or equal to epsilon, and we're going to write infinitely often. Okay, so this will consist of all sample points that violate the convergence requirement with this threshold epsilon. So that's why you have this infinitely often condition at this level epsilon. And then we observe that this event, E subscript epsilon, is a subset of E. Okay? And if you're confused by that, let me explain this again. E consists, basically, this is what E consists. This is the event of all sample points which do not converge to A. Now, I'm being a little bit sloppy here. I'm not really talking about the sample points. I'm talking about the sample points evaluated with these averages, but I'm trying to keep it short. So this is the event of sample points which do not converge to A, whereas this is the event of all sample points which do not converge to A at this epsilon threshold. The difference between these two is, as we remarked in our quick advanced calculus review, that if a sequence does not converge to the limit, then there is some positive number, some positive threshold number that violates the convergence inequality. This is a subcollection of those sample points which fail to satisfy the convergence of the inequality at this epsilon level. Okay, whereas this is the collection of all of them. So this is a subset of that. And since the probability of E is 0, because this is what we are assuming. We are assuming the probability of those sample points, that event, occurs with probability 0. It will therefore mean the probability of this event. It will imply that the probability of this event, which is bounded by the probability of that event, is 0. And so the probability of the event E subscript epsilon also happens with probability 0. Okay, so we have shown that the probability of the following event, and let's just write out what this event is. This event, we've written it over here, so let's write it again. This is the collection of sample points, so that an of omega minus a greater than or equal to epsilon, that this event happens with probability 0. So this is what we have shown. What do we want to show? But we want to show something similar, but it's not exactly this. We rather want to show that the probability of the event where an, where this, and when you take the limit of those, that is equal to 0. So that's what we want to show. Oh, I made a small little mistake. I left out a very important point. You see, I forgot to say infinitely often, so I forgot to say, that's an important point. So let me write that again. Infinitely often. Whereas this one, it's this at level n without infinitely often. So they are a little bit different. They're not the same. And somehow, okay, so we've shown that the probability of this is 0. And somehow the question is, how do we go from one to the other? How do we go from what we have shown to what we want to show? How do we do this? So there's going to be a clever trick here in how we rewrite it. So let's write it in the following way. So we're going to construct the following event. Let's call this event E. So we have E epsilon n. And this is going to be the event, by definition. This is going to be the set of sample points with the property that a I of omega minus a greater than or equal to epsilon for some integer greater than or equal to n. Now, alternatively, you can also write it in the following way. You can also write this as the union, because you are saying for some integer bigger than n. So you can write it like this, I greater than or equal to n. And then you can write this as the event of sample points with the property that ai of omega minus a greater than or equal to epsilon. So this is a little bit ad hoc. It's not something that first comes to mind. But what happens when you construct these? So then you're going to observe that these events are decreasing. These are decreasing events. Why is that? Well, if you're located in the very first event, then you are saying that there's some integer larger than 1 that satisfies that inequality, right? Now, if you have an integer that is greater than 2 and it satisfies this inequality, then whatever that integer is, it's also greater than 1. So any sample point that falls in there falls in there. And for the same reason, if you have a sample point in here, then that means there exists some integer, right? Some integer bigger than 3 for which this inequality is satisfied. But if that integer is bigger than 3, then that integer is certainly bigger than 2. So this is a decreasing sequence of events. And if you take the intersection of all of those events, then that will actually give you exactly E subscript epsilon. And if you forgot what E subscript epsilon is, just to write that out, that is the collection of sample points, so that this inequality is satisfied infinitely often. Think about that. If you have a sample point that belongs to every single one of them, then that means you can go out as far as you want, right? You can go as far out as you want. There is no bound. You can go out as far as you want in the sequence of integers. So in particular, it has to happen infinitely often, that no matter what n you pick, there's always something bigger than that n for which it gets satisfied. That's what would mean infinitely often. So the intersection of all of this is exactly that. So this is the clever part of the proof. So this is, I would say, this part of the proof. This is the clever. That's not something that one would typically think of. That you're essentially what you're doing is you are taking this event that you had at the beginning of the proof, and you're writing it as this nested, decreasing collection of events in this clever way. And now we're going to use continuity of probability measure. This is something we've talked about earlier before, that if you can write an event as a decreasing collection, as the intersection of a decreasing collection, it will mean the probability of this is the limit of those probabilities. So then by continuity of probability measure, we have that if we were to take the limit of all of the probability of all of those events, that would be equal to the probability of E subscript epsilon. But we said the probability of this is 0 from before. And now we're almost done. And now finally, the event where an of omega minus a is greater than or equal to epsilon is certainly contained in this event, E. It'll be a good idea for me to write this out more carefully, because maybe you forgot the definition. AI minus A for some I greater than or equal to n. So, of course, this is a subset of that, because if this inequality is satisfied at n, well, you can then pick for this integer I, you can then pick I to be n itself. And what is this? This is exactly, by definition, this is equal to, by definition, this is the way we defined it. This is the event E epsilon n. So the limit, when n goes to infinity, of this event is therefore dominated. You see, this event is dominated by that event. But the limit of all of those is 0. So that would mean the probability of those is also equal to 0. And that's exactly the law of large numbers, because we sometimes get sloppy and we just rewrite this as an minus a greater than or equal to epsilon. That's the shorthand way of writing that. So then the probability of that event, the limit of those probabilities, will converge to 0. And that's exactly the weak law of large numbers. So as you can see, we have shown that if we assume the strong law of large numbers, then we get the weak law of large numbers. It's not true the other way around. And now what we have to do is we have to prove, this is the last remaining proof, is we have to prove the strong law of large numbers in the special case when we have a random walk. Now we prove the strong law of large numbers in a special case. a special case of the strong law of large numbers, which is relevant for us because this has to do with random walks. We assume that we have a sequence of independent random variables, and they all have the same distribution. And more specifically, is that these are independent coin flips, so that the probability that xn is equal to plus or minus 1 is equally likely to happen. And then we're going to set an to be the empirical average of the first n tosses. We will prove that the probability, so if we were to look at the set of sample points, so that the limit of an at those sample points does not converge to 0. So in this case, all of these random variables, their expectations are 0. If we were to find that event of all such sample points, then the probability of that event would be 0. So it does consist of sample points which violate this limit, but the event of all such sample points has probability 0. And as you will see in the course of the proof will not be able to generalize to the case where you have a more general random variable, a sequence of random variables that are independent. You will actually use this somewhere in the course of the proof. So it's not a proof that generalizes, but it would be sufficient for our purposes. And the proof will be somewhat similar to what we just proved when we showed that the strong law implies the weak law. There will be a lot of overlap between the two. And I also want to say that we're going to secretly use something called the Borel-Cantelli lemma in disguise. I'm not going to tell you what that lemma says. I do not want to provide additional facts from probability theory beyond what we need. So I'm going to present the proof that will appear to circumvent this lemma, but not really. The reason why I bring this up is because if you open up a book on probability theory and you look at the way they prove this, you will notice they keep on referencing this, and then you may wonder, why did we manage to do it without using that lemma? Not really. It's just that we're doing it in a very disguised way. So here's how the proof is going to go. That so we can write it like this. So the event consisting of sample points, so that the limit of these random variables at the sample point do not converge to 0. It means that it goes back to what we were saying about advanced calculus, that you have a sequence, and if the sequence does not converge, in this case does not converge to 0, then it will mean that this inequality, an epsilon, so an of omega, will have to be greater than or equal to some epsilon. And this has to happen infinitely often. So we can write it like this. We can say that this is equal to the set. I'll just write it like this. It'll be the event consisting of the set of sample points that violate the epsilon inequality, because we're saying something converges to 0, so in absolute value it can be made arbitrarily small. So if it does not converge to 0, that means it will have to be greater than or equal to some number epsilon, and this happens infinitely often. But of course, this is just for a single epsilon. If something does not converge to 0, then that means there exists an epsilon. So if you have a sample point so that the sequence does not converge to 0, that means it has to satisfy this condition for some epsilon. So for some epsilon, so you have to unionize all those epsilons. So then we would have to take the union of all epsilon bigger than 0. That's what we would have to write it. So the set of points for which the sequence does not converge to 0 would mean that this inequality is satisfied for some epsilon. So that's why we have a union, because it's for some epsilon. And this inequality has to occur infinitely often. Now, in probability theory, we like to use countably many objects. And there's a little bit of an annoyance here that this is indexed by a real number. So to fix this, you can assume, without loss of generality, that the epsilon is rational. So you can just assume it's a rational positive number. The reason is very simple, because if something is bigger than a real number, you can find a smaller rational number, and it will be bigger than that smaller rational number. So you can always make the epsilon smaller and replace it by a rational number. So without loss of generality, we can just assume this is a countable union. So why are we doing this? Well, because we want to show the probability of this is equal to 0. So thus, the probability of this event, and I'm going to stop writing omega in the sample space. I'll just write this. So the probability of the event where an of omega is not 0, it is less than or equal to, because it's a countable union. Usually the probability of a union, well, I should say this, the probability of a disjoint union is the sum of the probabilities. Here, these could overlap. These events could overlap. So that's why it's less than or equal to the sum of epsilon positive and rational. And then you have the probability of the event where an of omega is greater than or equal to epsilon infinitely often. So there's infinitely many different choices for n that will satisfy this type of inequality. Okay? And now the idea is really this. The idea is to show that the probability inside the sum that this probability happens, it's equal to probability 0. And then that would complete the proof, because then the probability of this event is less than or equal to 0, but it's not negative itself. So the conclusion is that the probability of that event is equal to 0. So that's what we have to show. And we're going to use a trick that we already used before. So previously, this is what we did in the previous proof. It's the same clever trick. We're going to, and this is really in disguise. That's why I mean the Borel-Cantelli lemma, but we're not saying what that is. You can look it up if you're interested. But previously, we constructed, so we're going to define E subscript epsilon. This is the event. This is the collection of sample points where an of omega is greater than or equal to epsilon infinitely often. And we're going to define another event, which is somewhat similar. We're going to call this one n subscript epsilon. And this is going to be almost the same thing with one small extra, well, with a small adjustment, that this is bigger than epsilon. And let me get rid of this n. This should be I for some integer I greater than or equal to n. And we saw that these events, en epsilon, these are decreasing events, and they decrease down to E subscript epsilon. This is just coming from the previous proof. It's the same setup as before. So what does that mean? Hence, the probability of E subscript epsilon, and by the way, this thing is exactly what we're calling this. You see, the idea is to show that the probability of that is 0. But the probability of this event can be expressed as the intersection. So you have this nested collection of events that are decreasing as the intersection of these. So this, by the continuity of probability measures, this would be the limit as n goes to infinity of p, e, and epsilon. And now we have to show that these have probability 0. So we have reduced the proof to show that if we take the limit as n goes to infinity of these events, that this is equal to 0. Now, recall that this event, you see, this event that we're writing over here, we're saying that we're satisfying this inequality for some integer bigger than or equal to this n. So this n is the cutoff point, and we're saying there exists an integer at n itself or beyond it that will satisfy this epsilon inequality. So because we're saying for some I bigger than or equal to n, we can therefore say that this is the union. So you're just going to write this as the union of events where the I ranges from n to infinity. So we would just say I ranges from n to infinity, and these would be the events where ai of omega is bigger than or equal to epsilon, like this. And we are taking the probability of this thing. So we're going to use the same idea that we used before. Then when you take the probability of a union, it will be less than or equal to the probability of the sum, because these could be overlapping. So thus, the probability E n subscript epsilon is less than or equal to this sum. ai of omega greater than or equal to epsilon. Oh, I forgot to say the probability of those. So I'm going to just write it like this, the probability of ai. And I forgot to write down absolute value. Not that it really, not that it really mattered, but I should have kept it there. So this should be the absolute value of these. And I'm going to suppress notation. I'll just write ai greater than or equal to epsilon, like that. Okay, so, and we're taking the limit of this, and we want to show it's 0. So we therefore have to show that the limit of this goes to 0. So we have reduced the proof to showing that if you were to take the limit as n goes to infinity of this sum, that it goes to 0. Now, what you should realize about this is that whatever this thing is, that thing, this is the tail. This is the tail of the infinite series that goes from 1 to infinity, and the sum of these probabilities. That's what that is. That is the tail. And this is just a well-known fact about infinite series. So a well-known fact about infinite series is that if an infinite series converges, actually it goes both ways, is that an infinite series converges so a series of numbers. And let me be very careful here. When you're working with infinite series, when you're working with non-negative infinite series, they generally behave a lot better. When you have positive and negative numbers, sometimes strange things happen. But here, these are probabilities after all. So these are non-negative numbers. So if you have a sum of an infinite sum of non-negative numbers, that this infinite series of non-negative numbers converges if and only if the tail, so this is the tail, goes to 0 as n goes to infinity. And really what this has to do with is this is sometimes called the Cauchy criterion. So I assume you have seen something like that. If not, you will have to look it up somewhere. You can try showing it yourself, but this is the fact that we're going to be using. Okay, so basically, so we have reduced the proof. So we have reduced the proof again. So we have kept on reducing this proof many times to showing that the following sum converges, where epsilon is an arbitrary positive rational number. The fact that it's rational is completely irrelevant. It's just that we set it up that way. And it does not matter what letter to use. I'm just going to use the letter N because I'm going to use the letter I later on for something else. Really makes no difference. So far, you can argue that everything we have done generalizes to any collection of random variables that satisfy the conditions that we currently have. But now you're going to see that we're really going to take advantage that we have a random walk. And this is what makes this proof special. So we're going to look at this again. And as in the proof of the weak law of large numbers, so if you go back to the proof of the weak law of large numbers, we squared both sides. But now we're going to raise everything to the power 4. So now, so this is the clever part of the proof. The probability that an in absolute value is greater than or equal to epsilon can be rewritten as the probability that an raised to the 4 is greater than or equal to epsilon to the 4. You see, here we're raising everything to the 4 because that's what we need to make the proof work. If you go back, it's like I said, if you go back in the video and you look at the proof of the weak law of large numbers, the way we made it work out is we went to this inequality and we had to square it. But here we have to raise everything to the power 4. And now we have to recall what an is. An is the empirical sum. So this can be rewritten as the probability. So an is the sum. So it's x1 plus x2 plus xn raised to the 4, greater than or equal to epsilon to the 4. And this sum gets divided by n to the 4, but we can clear denominators and put it over here. So this is what we have. And now we're going to use Markov's inequality. We're going to say that this is less than or equal to, so this is where we use Markov's inequality from before. That this sum, that probability, this is a concentration probability, that the expectation of all of these, well, they have a certain expectation, and we're asking for the tail probability that this is larger than some number. So this is less than or equal to the expectation. So this is the Markov inequality. This is the expectation of the sum of all of these. Then gets divided by the threshold. In this case, it's epsilon to the 4, n to the 4. Epsilon here is just a constant. It's fixed in the argument. Now, here is what we do next. If we expand all of that we will have a sum of terms involving x to the I. This is the reason why I wanted to keep I. X to the I, x to the j, x to the k, x to the l. Okay, where 1 is less than or equal to I, less than or equal to j, less than or equal to k, less than or equal to l, less than or equal to n. So you could have, for example, because you're using 4 of them, so you could have, for example, okay, so for example, you could have x1, 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 so x1 to the 4th. At the other extreme case, you can have xn, 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 xn. But then you can have x1, x1, x2, x2. We could have x1, x2, x2, x3, and so on. So that's what I mean. There's 4 of them. Now, here is the part which is very important. That if I, j, k, and l are distinct integers, then, and here we're going to use independence. By independence, the expectation of their product is equal to the product of their expectations. This is where independence becomes important. But the product of their expectations is 0 because each of these has expectation 0. Now, to use another example, also, if you have the expectation of xi, and let's say you have xj and k are equal, so j squared, then you have xl, then that would be equal to the expectation of xi, expectation. Now, when you square it, that just becomes 1. Because these random variables, they're either plus or minus 1. So when you square them, they become 1. So that would just be expectation of xi, expectation of xl, which would be 0 again. Okay, so what does that mean? So this means that the expectation of this sum is equal to, and I would say this, only terms of even powers. So here you have odd powers, and when you take their expectation, so when you take the expectation of this entire expansion, it's the expectation of the sum. But if you have odd powers, you get 0 expectation. Here you get 0 expectation. The only ones that's going to give you something non-zero is if they're even. And there's only 2. So you can have xi to the 4th. This is when you have the same index appearing 4 times, or you have xi squared, xj squared. That's the only contribution that you get in the expectation that is non-zero. And you have to realize that whatever this is just equal to 1, because xi is either plus or minus 1, and it's being raised to the power 4. This is 1. You're taking plus or minus 1 and you're squaring it. This is 1 and this is 1. Okay? Now, we're going to do a little bit of counting. The number of terms of the form xi to the 4th is exactly n. You have n different integers from 1 to n. And the number of terms of the form xi squared, xj squared, where I and j are different, is exactly, and if you want, you can pause the video and see if you can figure it out. It is a little bit tricky. You have to be comfortable with combinatorics, but for those of you who are interested, it is, first of all, you do n choose 2, because you have to choose 2 of them out of n of them. But then it's not that simple, because you also have to choose which integers you want to pick. And you have, you see, you have, well, I should say it like this. You have 4 of these, and you're choosing 2 that you want to take. So really what it is, it's n choose 2, 4 choose 2. That's what it is. So you have to work this out. So this is n choose 2. When you simplify that, that's n minus 1 over 2. And 4 choose 2, when you simplify that, that is 6. So you get 3n minus 1. So thus, the expectation of this expansion, when you work all of this out, this is going to be n. You see, every one of these terms, their expectation contributes n. And every single one of these terms, when you square them, it's just 1. It's the expectation of 1, the constant random variable 1. So it's 1, but how many do you have? You have that many. So it's plus 3n minus 1. So this is 3n squared minus 3n plus n. So 3n squared minus 2n. And for simplicity, we can just say it's less than or equal to 3n squared. Just drop off the negative 2n. So this is like the more important part, because this is the larger power. This is the less important term. So that's less than or equal to 3n squared. So let's take advantage of this and scroll all the way back up again. So this is how it came up. We have to find the expectation of this. And what we see is that this is bounded by 3n squared. So this entire expectation is bounded by 3n squared. And then it gets divided by epsilon to the 4, n to the 4. So this is just some constant divided by n squared for some positive c. And now we can remove all of the work that we did below, because it's no longer necessary. That was just to justify this inequality. And now we can return back to this probability. So thus, this series, where you're calculating the probability that an is bigger than or equal to epsilon, can be dominated by the series. And then we have this chain of inequalities, and in the end we get that it's dominated by c over n squared. And whatever that is finite, it converges, because it's well known that the series consisting of 1 over n squared is a convergent infinite series. And there we go. This concludes the proof of the strong law of large numbers. It's in the special case when you have a random walk. I think it's a very nice proof. It's a very interesting proof. Unfortunately, it does not generalize beyond that, but at least in the context of what we're doing, I think it's a very nice proof. It's nice to see that a little bit of counting has to be involved to get those estimates. So with that, we've concluded with today's lecture.